I'm Paul.
I'm Bobby.
And I'm Andrea. And for our project, we decided to focus on hexaflexagons.
Take a look. For this section of the project, I want to talk about the actions we took. So, how to create a flexagon and some of the definitions that we came up with.
This is a flexagon. It's a 2D object, but has 3 sides or faces. You can change the sides or faces. It's not like a cube, or a circle, or a triangle. All the sides face up. You can only see one side at a time. This shape is fun to explore, so let's check it out. To distinguish a side, we used a different color or number in this case. So, for example, this is side 1. This is side 2. And this is side 3. For this inquiry, the technique we used to fold was a pinch, flatten, and pull method. So let's see that. Pinch, flatten, and then pull. That's how we change sides for every flexagon we encountered. This is how you start a 3-sided flexagon. We have a strip of paper consisting of 10 triangles. That means that this has a strip length 10. I'm going to show you how to fold it up. It's pretty easy. Just like so. And then go ahead and fold this under. And then tape the other side down. We did most of our initial inquiry using the 6-sided flexagon. This has a strip length of 19, so 19 little triangles in a long line. It's a little longer than the 3-sided one, and it's more complicated to fold up, and we got really good at folding them up. But there are many things to explore and observe with the 6-sided flexagon, a lot more phenomena to understand, and a lot more sides to play with. I'm going to show you how to fold it up right now. We also tried to make a 4-sided flexagon of strip length 13, but it didn't work. We also made conjectures using strips of different shapes and sizes, but usually they didn't work either. If these strips of odd shapes did follow our strip length to side face algorithm, which we'll talk about later, they were usually difficult to fold up into a working flexagon. We also found a way to map the paths of the sides. The flexagons are oriented in different ways, but there's some order and relationship between sides. We set up a simple diagram to show you how the sides are set up. We'll talk about our findings later in this video.
Okay, now let's take a closer look at what these flexagons can do and how they work.
Okay, here we have a 6-sided flexagon. So there's sides 4, 6, and 5. And that makes up the core of our flexagon, as seen here, which is you can cycle between any of these 3 sides. Now, from sides 4 or 5, we can get to branch 3. So in order to get from branch 3 to any of the other branches, we have to go through the core, as seen here. Now we have sides 4 and 6. And that will get us to branch number 1. And there is no way to go through straight from 3 to 1 without going through the core and getting 4 and 6 as the 2 faces. Now we have 5 and 6 as our 2 faces, which gives us our 3rd branch of 2. And the mapping is done.
Okay, I will now draw the mapping of the 6-sided flexagon. We will start with the core of 2, 3, and 4. These are the basic sides and the easiest to get to. On the reverse side is 5, 6, and 1. We call these the branches. Now there's no way to get from one branch to the other. However, you can always get back to the core from any of the branches. The branches are a little harder to get to. When we unwound the 6-sided hexaflexagon, we noticed a pattern on the numbering of the sides. For instance, on this side, we saw that all the numbers were doubled. 5, 5, 6, 6, 1, 1, on and on and on. Now when we flip the strip over, we can see a repeating group of 3 numbers, 2, 3, and 4, all the way down. We have our mapping for the 6-sided, but we also managed to make maps for the 3-sided, represented here. As you can see, the 3-sided is nothing but the core, and a 5-sided. The 5-sided has the same core, 1, 2, 3, but also the 2 branches are 4 and 5, and as you can see, just like from the 6-sided one, there's no way to get between branches 4 and 5. You have to go through the core. We saw a relationship between the number of possible sides and the length of the strip. And as we worked with them more, we came up with a formula relating the strip length and the number of sides, which goes that the strip length minus 1 divided by 3 is equal to the number of sides.
Template for a 3-sided gave us a strip length of 10. For a 6-sided, it gave us a strip length of 16, and for a 12-sided, it gave us a strip length of 37. Now, one of those sides gets eaten up by the folding and taping process, so then that gives us 9, 15, and 36 respectively. So we're looking for a number to get us from 9 to 3 and from 5 to 6, 36 to 12. And what we found was this pattern of 3 showing up again and again and again. So we just thought that, what would happen if we divided it by 3, and that worked. We didn't really have a reason beforehand to choose 3, it just happened to work out.
So after we analyzed all of our results, we wanted to see if there was a way we could use our formula that we created to predict higher order flexagons. So with this formula, we predicted that a flexagon with 12 sides would approximately need 37 triangles in the strip.
The strip looked like this, connected in the middle by another piece of tape. We coiled it around itself 2 times with the same technique used for the 6-sided one. So it was the length of 9 triangles, but had multiple layers. Then we folded it like the other ones. We had multiple attempts at the 12-sided flexagon, but it wouldn't fold right because of how we taped it. But then we finally got it. Gave us more proof that our formula worked and showed us that we can predict the number of sides for higher order flexagons. Through this, we discovered that there's still room to explore. We saw with the 5-sided hexaflexagon that there are multiple templates to build from. Therefore, some of the higher order flexagons might not use a straight strip. We also wondered if it was possible to build a flexagon with shapes other than isosceles triangles. We did find some templates for right triangles online and could use those to push the inquiry process further.